These two objectives will be covered in two parts. At the end of this part 2 video, you should be able to fully define atomic and ionic radii, ionization energy, electron affinity, and electronegativity, and compare the periodic trends of atomic radii, ionization energy, and electronegativity, as well as state the reasons for these variations, with the exception of electronegativity, which will be covered in the next video. Chapter 5, Section 3, Electron Affinity. Neutral atoms can also acquire electrons. The energy change that occurs when an electron is acquired by a neutral atom is called the atom's electron affinity. Most atoms release energy when they acquire an electron. In your textbook, the quantity of energy released is represented by a negative number. On the other hand, some atoms must be forced to gain an electron by the addition of energy. The quantity of energy absorbed is represented by a positive number. An ion produced in this way will be unstable and will lose the added electron spontaneously. Figure 5-17 on page 147 of your text, or on the screen now, shows the electron affinity in kilojoules per mole for the elements. Figure 5-18 on page 148 of your text represents these data graphically. Period trends. Among the elements of each period, the halogens, group 17, gain electrons most readily. This is indicated in figure 5-17 by the large negative values of halogens' electron affinities. The ease with which the halogen atoms gain electrons is a major reason for the high reactivities of the group 17 elements. In general, as electrons are added to the same p sublevel of atoms with increasing nuclear charge, the electron affinities become more negative across each period within the p block. An exception to this trend occurs between groups 14 and 15. Compare the electron affinities of carbon, which has an electron configuration of helium 2s2 2p2, and nitrogen, which has an electron configuration of helium 2s2 2p3. Adding an electron to a carbon atom gives a half-filled p sublevel. This occurs much more easily than forcing an electron to pair with another electron in an orbital of an already half-filled p sublevel of a nitrogen atom. Group trends. Trends for electron affinities within groups are not as regular as trends for ionization energies. As a general rule, electrons add with greater difficulty down a group. This pattern is a result of two competing factors. The first is a slight increase in the effective nuclear charge down a group, which increases electron affinities. The second is an increase in atomic radius as you go down a group, which decreases electron affinities. In general, the size effect predominates, but there are exceptions, especially among the heavy transition metals, which tend to be the same size or even decrease in radius down a group. Adding electrons to negative ions. For an isolated ion in the gas phase, it is always more difficult to add a second electron to an already negatively charged ion. Therefore, second electron affinities are all positive. Certain p-block nonmetals tend to form negative ions that have noble gas configurations. The halogens do so by adding one electron. For example, chlorine has a configuration of neon 3s2 3p5. An atom of chlorine achieves the configuration of a noble gas, argon, by adding an electron to form the Cl-1 configuration, which is neon 3s2 3p6. Adding another electron is so difficult that Cl2- never occurs. Atoms of group 16 elements are present in many compounds as 2- ions. For example, oxygen, the configuration of helium 2s2 2p4, achieves the configuration of the noble gas neon by adding two electrons to form the O2- ion, which has a configuration of helium 2s2 2p6. Nitrogen achieves the neon configuration by adding three electrons to form the ion N3-.
Some elements acquire electrons to form negative ions. In the case of chlorine, the formation of a negative ion is favored because the resulting chlorine has a full octet. In general, the closer the atom is to acquiring a full octet, the more strongly it attracts electrons. Chlorine has 7 valence electrons, and its electron affinity is negative 361.7. By convention, the more negative the number, the more strongly the atom attracts the negative electrons. Phosphorus has 5 valence electrons and an electron affinity of only negative 74.6. The electron affinity of aluminum, with 3 valence electrons, is negative 44.1. Because of the way electrons form orbitals, there are some lapses in this pattern. Nevertheless, the general trend holds.
Ionic Radii. Figure 5-19 on page 149 of your text, or on the screen now, shows the radii of some of the most common ions of the elements. Positive and negative ions have specific names. A positive ion is known as a cation. The formation of a cation by the loss of one or more electrons always leads to a decrease in atomic radius because the removal of the highest energy level electrons results in a smaller electron cloud. Also, the remaining electrons are drawn closer to the nucleus by its unbalanced positive charge. A negative ion is known as an anion. The formation of an anion by the addition of one or more electrons always leads to an increase in atomic radius. This is because the total positive charge of the nucleus remains unchanged when an electron is added to the atom or an ion. So the electrons are not drawn to the nucleus as strongly as they were before the addition of the extra electron. The electron cloud also spreads out because of the greater repulsion between the increased number of electrons. Period trends. Within each period of the periodic table, the metals at the left tend to form cations, and the nonmetals at the upper right tend to form anions. Cationic radii decrease across a period because the electron cloud shrinks due to the increasing nuclear charge acting on the electrons in the same main energy level. Starting with group 15, in which atoms assume stable noble gas configuration by gaining 3 electrons, anions are more common than cations. Anionic radii decreased across a period for the elements in groups 15 through 18. The reasons for this trend are the same as the reasons for cationic radii decrease from left to right across a period. Group trends. As they are in atoms, the outer electrons in both cations and anions are in higher energy levels as one reads down a group. Therefore, just as there is a gradual increase in atomic radii down a group, there is also a gradual increase of ionic radii. At this point, you should be able to fully define atomic and ionic radii, ionization energy, electron affinity, and electronegativity, and compare the periodic trends for atomic radii, ionization energy, and electronegativity, as well as state the reasons for these variations, with the exception of electronegativity, which will be covered in the next video.